Hello students. Today we start to study the power system voltage and reactive power integrated automatic control device. In the previous chapter, we learned that under normal circumstances, the system frequency is the operating parameter of the power system to maintain consistency. The grid frequency is determined by the generating power and the magnitude of the electrical load. When the generating power and the magnitude of the electrical load are equal, the grid frequency is stable. When generating power is greater than the electrical load, the grid frequency increases. When generating power is less than the electrical load, the grid frequency decreases. To keep the frequency constant, the rotational speed of the generator must be kept constant. And to maintain the rotational speed of the generator constant, we must maintain a stable load by adjusting the active power of the generator. The balance of power supply and demand in the system can be maintained so that the frequency can be maintained in a small range of change. Similarly, in the power system, due to the user load and grid configuration changes, the voltage loss of the grid will also change. Ensure the stable operation of the grid voltage is one of the primary tasks of the power system operating adjustment. So, what are the connections between system voltage and reactive power? Let's look at this diagram. This diagram shows the relationship between the load and the compensator in our single-phase distribution system. In the figure, U is the system voltage, R and X are the resistance and reactance of the system. We assume that the load varies very little, so the voltage varies very little, of course. We also assume that the system resistance is much smaller than the system reactance, according to which it can be drawn in the figure on the right, that is, a diagram showing the relationship between system voltage and reactive power. We can see from the figure that the more reactive power the system supplies and exchanges to the load, the more the supply voltage decreases. We know that the system voltage U satisfies the following relation, that is, U equals to U0 multiplied by 1 minus Q divided by Sk. Sk in the above equation is the short circuit capacity of the system. We differentiate both sides of the above equation at the same time and then convert it into a function to change the variable. We can get du equals to negative U0 multiplied by dq divided by Sk. Delta U divided by U0 equals to negative delta Q divided by Sk. That is, when the reactive power on the right changes, the system voltage also changes, and the two changes are proportional to each other. We know that the total reactive power of the system is equal to the sum of the reactive power of the load and the reactive power of the compensator. That is, Q equals to QL plus QB. If the load reactive power QL changes, the compensator QB can also change somewhat to compensate for the change of QL, so it can maintain the system voltage U unchanged. So there is a Q equals to constant. This is a principle of dynamic reactive power compensation, especially in the figure on the right. If the reactive power compensation can compensate Q close to 0, that is, at 3 points in the figure, this is a conventional full compensation of reactive power. It can be seen that the main difference between conventional reactive power compensation and dynamic reactive power compensation is that conventional reactive power compensation always tries to eliminate the reactive power to the minimum, making the power factor close to 1. Dynamic reactive power compensation, however, is to set the value of natural reactive power in the system to the optimal value, and use the method of reactive power compensation to make the value of this natural reactive power to remain unchanged, which achieves the purpose of stabilizing the system voltage. Reactive power is more abstract. It is the electrical power that is used to exchange electric and magnetic fields within a circuit and is used to establish and maintain magnetic fields in electrical equipment. It does not perform work externally, but is transformed into energy in other form.
When a current flows through a coil, it generates a magnetic field, converting electrical energy into magnetic energy and absorbing power. If the current decreases to zero, the magnetic field will also diminish until it disappears. The coil converts magnetic energy back into electrical energy, emitting power. During this process of absorption and emission, energy is not consumed, so it is called reactive power, meaning power without consumption. The same principle applies to capacitance, except that it can convert electrical energy into electric field energy. In addition, when an inductor absorbs power, the capacitance will emit power. So they can compensate for each other.
Any electrical device with a solenoid coil has to consume reactive power to establish a magnetic field. For example, our 40-watt fluorescent lamps, in addition to the need for more than 40 watts of active power to light, also need about 80 var of reactive power for the ballast coil. To establish an alternating magnetic field, it is called reactive power because it does not work outward. Power system reactive power compensation and the reactive power balance are the basic conditions to ensure the voltage quality. In this process, some important principles need to be observed, namely the principle of layered and zonal compensation, the voltage qualification standard, and the principle of reactive power compensation allocation. The principle of layered and zonal compensation is in view of the larger impedance. The transmission of reactive power will produce a large amount of reactive power loss and the corresponding active power loss. The grid reactive power compensation arrangements should be implemented by the principle of layered zonal and local balancing. The so-called layered arrangement refers to the main active power large capacity transmission, that is 220 kV to 500 kV grid. It is desirable to strive to maintain the balance of reactive power between the various voltage layers, as far as possible to make the reactive power crosstalk between these layers is very small to reduce the large amount of consumption of reactive power transmission through the power grid transformers. The so-called zonal arrangement means that it is desirable to realize the zonal and local balancing of reactive power in the power supply network of 110 kV and below. Voltage qualification standards refers to the different voltage levels have different voltage qualification standards. For the 500 kV bus bar in normal operation mode, the maximum operating voltage shall not exceed plus 10% of the rated system voltage, and the minimum operating voltage shall not affect the synchronization stability of the power system voltage stability, the normal use of plant power, and the next level of voltage regulation. When the 220 kV busbar of the power plant and 500 kV substation is in normal operation mode, the permissible deviation of voltage is 0 to plus 10% of the rated system voltage, and when it is in accident operation mode, it is minus 5% to plus 10% of the rated system voltage. For 110 kV to 35 kV bus bars of power plants and 220 kV substations, when in normal operation, the permissible deviation of voltage is minus 3% to plus 7% of the corresponding system rated voltage, and plus or minus 10% of the rated voltage of the system after an accident. The 10.6 kV bus bars of substations with regional power supply loads and power plants directly subordinate to them. The permissible deviation of voltage in the normal mode of operation is 0 to plus 7% of the rated voltage of the system. The third is the principle of reactive power compensation allocation, refers to the selection of the group capacity of reactive power compensation devices in substations of various voltage levels should be determined based on calculations. The maximum voltage change of the busbar caused by a single group of reactive power compensation devices switching should not be more than 2.5% of the rated value of the voltage and meet the maximum load of the main transformer. The power factor should not be less than 0.95. Well, class, that's all for today's lesson. See you in the next class.